Last time, we saw that electrical systems have the same basic characteristic behavior as mechanical systems. They have exponential solutions and, with an inductor, can experience oscillation. Today I want to go through an example that will help you get more comfortable with analysis of circuits. Let's say that we have a circuit that has 2 inductors and 3 capacitors. So I'm going to use a flow convention like this, and I'm going to label these I1, I2, and I3. I can assign the current sign convention any way I want, and then the way that I mark this represents that convention. Kirchhoff's current law states that we know that I1 is equal to I2 plus I3. Now, the voltage law states that VL1 plus VC2 plus VC3 is equal to 0, and VC4 plus VL5 minus VC3 is equal to 0. So this is around the left loop, and this is around the right loop. I could choose to sum around the outer loop if I wanted. Notice that in the second KVL equation, the sign of VC3 is negative. This is because the right-hand loop, going clockwise, encounters the negative terminal of C3. Also note that we know that I1 is equal to I L1, which is equal to Q C2 dot. We also know that I2 is equal to Q C3 dot, and we know that I3 is equal to I L5, which is equal to Q C4 dot. This means, just as in lecture 19, Kirchhoff's current law implies that KCL says that QC3 dot is equal to QC2 dot minus QC4 dot, and that implies that QC3 is equal to QC2 minus QC4 plus a constant that we'll assume is 0. The consequence of this is that we can use Kirchhoff's voltage law to find an ODE that governs the state evolution of the circuit. Keep in mind that the current through the left inductor is the same as the current through the left capacitor, and that the same thing holds for the right inductor and right capacitor. We get L1 times QC2 double dot plus 1 over C2 QC2 plus 1 over C3 times QC2 minus QC4 is equal to 0. We also get that L5 times QC4 double dot plus 1 over C4 QC4 plus 1 over C3, this should actually be a minus 1 over C3 times QC2 minus QC4 is equal to 0. If we convert this second-order differential equation to a first-order differential equation and choose the state vector to be W equals QC2 dot QC4 dot, we can then rewrite the differential equation in vector and matrix notation. And we get W dot is equal to, and now I need to write this relatively large so that we can fit all the terms. We have 0, 1, 0, 0, and then minus 1 over L1 C2 minus 1 over L1 C3, 0, 1 over L1 C3, 0. Then the next line is 0, 0, 0, 1, and then down at the bottom row, we get 1 over L5 C3, 0, and then minus 1 over L5 C4 minus 1 over L5 C3, and then the last element is 0. And this whole matrix multiplies W. And so to keep these separate, I'm going to draw a line down the board. This means that we have an equation of the form W dot equals A times W. So we can use Euler integration to approximate solutions or exponential solutions to obtain analytic solutions. Lastly, let's set all the constants equal to 1. That means that we have A is equal to 0, 1, 0, 0, minus 2, 0, 1, 0, 0, 0, 0, 1, and 1, 0, minus 2, 0. What do you expect the system to do, and how do you expect it to behave? I can take A and use MATLAB or Python to compute the eigenvalues of A. We know that these eigenvalues and the eigenvectors that go with them are part of the exponential solution e to the ht w from lecture 12. If I compute these eigenvalues, I get that h is equal to plus or minus the square root of 3 times j, or plus or minus j. This means that I should expect oscillation at two different frequencies, sine and cosine terms with frequencies of 1 and square root of 3. Since superposition applies, because this is a linear, constant coefficient differential equation, we know that I can also expect to sum these sine and cosine terms at the two frequencies. If there was a battery that was oscillating the voltage at some third frequency, then I know by the convolution equation that I should expect those frequencies to show up as well. What should we remember from today? We can use all the tools that we learned in mechanical systems, including vector and matrix notation and eigenvalue computation, to analyze and compute solutions for differential equations for electrical systems. Next time, we are going to talk more about analogies between electrical and mechanical systems to strengthen our intuition about the parallels between them.